Hi, in this lecture we will deal about the electrostatic field and its some properties and some idea about the electric potential. Now, first of all we will check whether the electric field is a conservative force or not. What are the conditions for a force to be conservative or a field to be conservative? For a force field to be conservative, work done by the force along a closed path is always 0 and curl of the force must be 0. For that, we have the electric field produced by a point charge q at a distance r is given by the equation E is equal to q by 4 pi epsilon 0 into 1 by r square r cap. This we have discussed in the earlier lecture. So, let this charge is kept at the center or at the origin of the xy coordinate system. Now, a point charge, that means a plus 1 coulomb charge is moving from one point to another point, that is from the point A to the point B. Let it be on this point, the point A to point B. I can take this charge from point A to point B and any path along this path or along this path. Now, what is the position vector to the point A? The position vector to the point A, I am naming it as RA, and the position vector to the point B, I am naming it as RB. So, what is the total work done in moving this charge? So, the work done we can write it as work done, we know that W is equal to F dot S. This is the basic equation for the work done. So, this force developed is equal to the electric field, since it is plus 1 coulomb charge. So, which is equal to E, and if the charge is moving, this plus 1 coulomb charge is moving in a dl distance, then that small work done to move the charge through a distance of small elementary length dl, dw is equal to E dot dl, E dot dl. So, the total work done must be integral E dot dl, integral E dot dl. So, dw represents the small work done and the integral will give you the total work done. So, in which coordinate system we will choose this dl? In most of the cases, we will choose this dl in the spherical polar coordinate system. And in mathematics, you have learned how can you write this small elementary length dl in terms of r, theta and phi. So, we can write dl as dr r cap plus r d theta theta cap plus r sin theta d phi phi cap. So, this is the dl in spherical polar coordinate system. So, the curl of a force is 0, and if the work done by the force along a closed path is 0, then such a force field is conservative force field. So, we know that what is E? E is equal to q by 4 pi epsilon 0 into 1 by r square into r cap. So, I am substituting this equation, this E and dl in, this E and the dl equation in this work done, which is equal to E dot dl. So, I can write it as W is equal to q by integral q by 4 pi epsilon 0 into 1 by r square into r cap dot dl, dot dl. So, which is equal to integral q by 4 pi epsilon 0 into 1 by r square into this, only this r cap term will survive, all other term will become 0, because r cap dot theta cap is equal to 0 and phi cap dot r cap is also 0. So, only the first term will survive, that means q by 4 pi epsilon 0 into 1 by r square into dr. This is the work done. But how will we choose the limit? We should choose the limit of r from Ra to Rb, because we are moving from the point A to point B. But if you rotate, if you start from A and then you come again to the point A, so what is happening is Ra will become Rb. That means you have completed one rotation. In that case, Ra is equal to Rb, then W is equal to, you will get it as, since both the limits become same, you will get it as minus q by 4 pi epsilon 0 into 1 by r, the limit from Ra to Rb, and we know that Ra and Rb are equal, then the total work done is equal to 0. So, this is how we are proving the work done along a closed path is 0. So, that means the total work done by the E depends only on the initial and final points. If the initial and final points are not the same, then the work done is equal to q by 4 pi epsilon 0 into 1 by Ra minus 1 by Rb. That means the work done depends only on the initial and final point. So, we have this equation, closed integral around a closed path, I can write it as closed integral E dot dl is equal to 0. So, if the force field is a conservative force field, I can write like this, closed integral E dot dl is equal to 0. This proves that electrostatic field is a conservative field. Now, for this equation, apply the Stokes theorem. So, for this equation, if I am applying the Stokes theorem, what will happen? The closed integral E dot dl will become the area integral or the surface integral, which is equal to closed integral E dot dl is equal to surface integral del cross E dot d. This you know, and we know that closed integral E dot dl is equal to 0. That means integral del cross E is equal into dA is equal to 0. This dA can't be 0. So, in such a case del cross E must be 0. So, if the force field is a conservative force field, then del cross E is equal to 0. So, this is about the conservative force field, and this proves that the electrostatic field is a conservative force field. Now, if the electric field is E1 plus the sum of electric field produced by different charges, then E can be written as E1 plus E2 plus E3 up to En. Then what about del cross E? Del cross E is equal to del cross of E1 plus E2 plus E3 plus up to En. So, which is equal to del cross of E1 plus del cross of E2 plus del cross of E3 up to del cross of En is equal to 0, which is equal to 0. That means del cross E is equal to 0, we have proved just now. That means the total, whatever may be the electric field produced by individual charges, then also its curl must be equal to 0. That means del cross E1 must be is equal to 0 and del cross E2 must be equal to 0 and del cross E3 must be equal to 0. Del cross E1 plus del cross E2 plus del cross E3 individually, if they are 0, then del cross E1 and del cross E2 plus del cross E3 must be 0. Technically, the electrostatics can be considered as a study of stationary charge and the vector field called electric field induced by the vector field is having 0 curl and non-zero divergence. This is the main property or the main idea of an electric field. Now, we can learn what I mean by this electric potential. In the lower classes you have learned that, but now in detail we will discuss what is this electric potential. So, what is actually electric potential? Electric potential is defined as the work done in moving a unit positive charge from a reference point to a point in the electric field. Right. In the case of electric field, the reference point is taken as infinity. So, same just like what we have proved in the case of a conservative force field, we are considering a test charge moving in a field produced by this charge q. So, this q is at the origin and the field produced by the charge q at any distance r is equal to 1 by 4 pi epsilon 0 q by r square into r cap. And now, I am moving from a point A to the point B. A plus 1 Coulomb charge is moving from the point A to the point B with a small displacement dl, and the position vector to the point A is r a and the position vector to the point B is r b. So, the total work done dw is equal to F dot dl. Now, I can write it as dw is equal to E dot dl. And in the spherical polar coordinate system, this dl is nothing but, we know that r cap into dr plus r d theta theta cap plus r sin theta phi cap d phi. Now, the total work done is equal to integral E dot dl and the reference point are r a and r b. Now, initially I told you that the initial point we are taking is at infinity, the reference point we will take it as infinity, and this work done, the work done is against the field. So, I should put a negative sign. So, this initial point is at infinity and to the point r b, and I call which is equal to r, and it is equal to E dot dl, and this negative sign, that this shows that we are doing this work done against the field. So, and I call this work done as the electric potential V. So, electric potential is defined as earlier we have just defined the electric potential as the work done in bringing an unit positive charge from infinity to a certain point. So, the potential has the equation V is equal to infinity from infinity to a point r in the field and E dot dl. This integral E dot dl will give you the electric potential at that point. So, what is the final expression for this electric potential? I can substitute the value of E, I name it this equation as A and this equation as B. So, what is V? V I can put it as minus integral infinity to r, what is E? 1 by 4 pi epsilon 0 q by r square into r cap dot dl. Yes, we are done. Just for the conservative force, we can write it as minus integral from infinity to r 1 by 4 pi epsilon 0 is a constant. I can take this out, 1 by 4 pi epsilon 0 and q also is a constant, so I can take q outside, which is equal to 1 by r square, and as just in the earlier case we can only the first term will survive on taking the dot product between dl and this e, only this first term will survive, all other terms will become 0 on taking this dot product. So, which is equal to minus q by 4 pi epsilon 0 into r square into dr, and we will get it as 1 q into 1 by 4 pi epsilon 0 into this minus and this integration, there will be a minus sign which will become 1 by r into infinity up to this point, reference point r. So, on this integration we will get it as q by 4 pi epsilon 0 into upper limit is 1 by r minus 1 by infinity. So, what is this 1 by infinity? 1 by infinity is nothing but 0, which will give you the expression for the electric potential at a distance r, which is equal to 1 by 4 pi epsilon 0 into q by r. So, the electric field has a variation of 1 by r square, then the potential has a variation with distance as 1 by r. These are the two difference between the electric field and the electric potential V. So, this equation gives the expression for potential at a point with the position vector r, that in general potential can be written as V is equal to 1 by 4 pi epsilon 0 q by r, and where r is the position vector with respect to the source charge q. Now, we will discuss what is the potential difference. The potential difference is defined as the work done on a unit positive charge between 2 points. If the unit positive charge is moved from point A to point B, then the potential difference is equal to Vb minus V. That means you have 2 points, or in this diagram there you have 2 points A and B, this point A and point B, and you are moving this charge, unit positive charge, along this line with a displacement dl, then the potential difference is equal to the potential at the point B minus point A, which depends upon the negative sign, which depends upon which one is the higher potential and which one is the lower potential. So, this is the potential difference. So, again the potential difference is defined as the work done on a unit charge between 2 points. If the unit positive charge is from point A to point B, then the potential difference is Vb minus Va, and here the Vb is greater than Va. And if you are moving it through a continuous path, the same expression will come. Instead of this infinity, you should put it as some position vector Ri and position vector Rb. In the same case, you will get it as V is equal to from integral Ra to Rb minus is there 1 by 4 pi epsilon 0 into 1 by r square into r cap dot dl. And we know that only the first term will survive. So, I can write it as V is equal to minus integral Ra to Rb into 1 by 4 pi epsilon 0 into 1 by r square dr, and which is equal to minus, there will be a minus sign by this, on integrating this 1 by r square, that will become positive. That means, and there is one more thing, there is a q here. So, q by 4 pi epsilon 0 into 1 by r, and which is equal to Ra to Rb. So, which is equal to q by 4 pi epsilon 0 into 1 by Rb minus 1 by Ra. And if you check this equation, you can see that V is nothing but 1 by 4 pi epsilon 0 Q by RB minus 1 by 4 pi epsilon 0 Q by RA. That means V is equal to this, I can call it as VA, VB, and this I can call it as VA. This is what we are told in the first introduction part of electric potential difference. This electric potential difference is the work done in moving a unit positive charge from the point A to the point B. So, this is the expression for that potential difference, which is equal to VB minus VA, which is 1 by 4 pi epsilon 0 Q into 1 by RB minus 1 by RA. Now, an important session in this lecture is the electric field can be defined as the negative gradient of the potential. So, how can we prove that the electric field has a negative gradient of the potential? You can choose in two different ways. You can choose this verification whether the electric field is a negative gradient of the potential. Now, how I can do this mathematical proof for this statement? For that, what we are doing is we can consider this equation itself. What is the potential difference between these 2 points A and some other point A dash, and I call it as dV. The difference, the potential difference, I can call it as VB minus V. This potential difference dV, I can call it as VB minus V. Now, this dV can be represented in the spherical coordinate system and in terms of the partial differentiation. The dV can be written as dV is equal to dou V by dou R into dr plus dou V by dou theta into d theta plus dou V by dou phi into d phi. So, this is how I can represent this dV in the spherical polar coordinate system, and this can be proved as what is del V dot dl. You know that this del can be represented in terms of spherical polar coordinate system, that is del V is equal to what is del V? Dou V by dou R into R cap plus R into dou V by dou theta into theta cap plus 1 by R into dou V by dou theta into theta cap plus 1 by R sin theta into dou V by dou phi into phi cap. So, what is del V dot dl? And we know that dl is equal to R into what is R into R cap into dr plus R into d theta into theta cap plus R sin theta into d phi phi cap. So, I can find out what is del V dot dl, which will give you the result as dou V by dou R into R cap, and R cap will become 1 and 1 by R and this R will go, that is dou V by dou theta into d theta plus R sin theta, and R sin theta will go, and which is equal to d phi dV by d phi into dou V by dou phi into d phi into d phi. That this shows that del V dot dl can be represented as dV. So, what is dV actually? dV is nothing but integral E dot dl. So, which is the potential difference, which is equal to V. So, I can write it as integral del v dot dl is equal to minus integral E dot dl. So, I can write it as E is equal to minus del v. This is a proof for electric field is the negative gradient of electric potential. Electric field is the negative gradient of electric potential. Similarly, you can prove it using the Stokes theorem by taking the potential difference. Sorry, not on the Stokes theorem, the gradient theorem. So, according to the gradient theorem, it is very simple. VA minus VB minus VA is the V. So, for that you can write it as the same expression will come del V dot dl. For like that also you can prove this electric field as the negative gradient of potential. Now, we will discuss what is the potential due to an infinitely long wire. So, I am going to derive the potential, the value of the potential for an infinitely long wire having linear charge density lambda. So, the linear charge density for a wire is lambda coulomb per meter, and I want to find out what is the potential at a distance r from the center of this wire. We know that the electric field E is equal to 1 by 4 pi epsilon 0 lambda by r into r cap. This we have derived in the first lecture, that E is equal to 1 by 4 pi epsilon 0 into 2 lambda by r into r cap is the electric field produced at a point P at a distance r from the center of an infinitely long straight conductor. So, what is the potential? What is the potential produced at this point? For this potential, what we want to do is the reference point should not be at infinity, or it should not be at the point 0. That you will understand why we are not choosing this reference point as infinity or 0 in this case. So, by definition V is equal to minus integral the reference point, which is the infinity, into that point at the field r into E dot dl. So, which is equal to, I can simply write this as 1 by 2 epsilon 0 into integral lambda by r into r cap dot dl, and dl is equal to dr r cap plus r d theta theta cap plus r d phi phi cap, and one more thing is this sin theta into r d phi phi cap. So, in this case also only the first term will survive, all other terms will go, which is equal to 1 by 2 epsilon 0 into integral lambda by r into dr. So, what is the integral of 1 by r dr, which is equal to 1 by 2 epsilon 0, which is equal to lambda is there, which is equal to 1 by r dr is equal to log r, which is equal to log r. So, what about this reference point? If you choose this reference point is infinity, log infinity or log 0, that cannot be defined so easily, and it is not well defined also. So, I can write only a reference point, I can take it as a point A to a point R. So, the integral will become from the point A to the point R, which is V is equal to lambda by 2 pi epsilon 0 into log A minus log R with a minus. So, you can write it as lambda by 2 pi epsilon 0 into log r minus log a, log r minus log a. This is the potential produced by an infinitely long straight wire with the linear charge density lambda. Now, we will discuss what is the potential due to an spherical shell, and for a shell there are 3 points, one outside the shell, surface of the shell and at the inside of the shell. And the easiest thing is, the most of these 3 cases the potential will become constant inside and at the surface, and for the outside the potential will vary according to this distance r, and we will check how this potential will vary with distance. For that we will consider a shell of radius r. So, this is for an infinitely long straight wire, for an wire of linear charge density lambda. Now, we will discuss the potential due to an spherical shell, potential produced due to an spherical shell. I am considering a shell of radius r, considering a shell of radius r, and outside the point P I want to find out at a distance r from the center of the shell what is the potential produced at this point P. Same formula, same equations and the same idea, using V is equal to the reference point infinity to that field point r into minus integral E dot dl, minus integral E dot dl. Now, I can choose this reference point as infinity, and I can write V outside, V out is equal to from infinity to r minus E out dot dl, E out dot dl. What is the electric field produced outside the shell? We know that E out is equal to 1 by 4 pi epsilon 0 q by r square into r cap. Similarly, dl is equal to the spherical polar coordinate system dr into r cap plus r d theta into theta cap plus r sin theta d phi phi cap. So, for that we can write, or we can substitute these two values, only the first term will survive, and we got it as V out is equal to integral from infinity to point r 1 by 4 pi epsilon 0 q by r square into, only the first term will survive, that is dr. So, which is equal to 1 q by 4 pi epsilon 0 into this minus sign, and this minus sign will, on integration there will be an additional negative sign that will go, and only 1 by r will be there, and which is from infinity to r. So, I can write it as q by 4 pi epsilon 0 into 1 by r. This is the potential outside the point. But we know that if the surface charge density of the sphere is sigma, shell is sigma, then the total charge it can be written as q is equal to 4 pi r square sigma. I can substitute this value for q here in this equation for the potential, and I can write it as 4 pi r square sigma divided by 4 pi epsilon 0 into r. 4 pi and 4 pi will go, and we will get it as V is equal to sigma r square by epsilon 0 r. This is the electric potential produced outside the shell at a distance r from the center of the shell. What about the potential on the surface of the shell? On the surface of the shell, only one thing will change, only this integration from infinity to small letter r will change to infinity to the small letter, the capital letter R, where capital letter R is the radius of the shell. We will check what is the potential at the surface of the shell. For the potential at the surface of the shell, you will get it as V at the surface is equal to from minus infinity to capital R E at the surface dot dl. E at the surface dot dl. So, for that integration we take it as the general expression for the E out. So, you will get it as 1 by 4 pi epsilon 0 q by r into the limit from infinity to r, and this term you can try by yourself, which is equal to 1 by 4 pi epsilon 0 q by r. And if the surface charge density is sigma, and I can write q as 4 pi r square sigma by 4 pi epsilon 0 r. 4 pi and 4 pi will go, r and r will go. So, V is equal to sigma r by epsilon 0. In this case, or at the surface of the shell, V is a constant, that because sigma is a constant, uniform surface charge density, r is a constant, which is the radius of the shell, and epsilon 0 is also a constant. That means at the potential is a constant at the surface. Potential is a constant at the surface. We will check what is the potential inside the shell. The potential inside the shell is actually the sum of potential outside and potential inside the shell. So, how can I write the potential V inside? The V inside is nothing but V in is equal to integral minus is a common actually, minus integral from infinity to r E out dot dl plus integral from infinity to the small letter r, where r is the point inside the shell, which is equal to V in E inside dot dl, V inside dot dl. So, actually what is the potential produced inside the shell? The potential produced inside the shell can be due to the potential at the surface and at the potential inside. The electric field at the surface, there will be a potential due to this surface term and due to this inside. So, I can write it as, instead of this E out, I can take the limit as capital R. So, V in is equal to integral minus integral. You on this integration, you will get it as 1 by 4 pi epsilon 0 q by r plus what is the electric value of electric field inside the shell? Inside the shell, according to Gauss's law, we have proved that inside the shell the electric field is equal to 0. So, that means 1 by 4 pi epsilon 0, only the first term will survive, which is equal to 4 pi r square sigma by r. That means V inside equal to V at the surface, and the potential inside the shell is a constant, which has a constant value of the potential at the surface. So, V inside is equal to sigma r by epsilon 0, and V at the surface is equal to sigma r by epsilon 0. This is the potential produced at this outside, inside and at the surface of an spherical shell. Now, the most important thing is the Poisson's equation, and Poisson's equation can be derived easily from the idea of the concept of Gauss's law and from the concept of the potential as a negative, or sorry, the electric field as a negative gradient of the potential. So, how can I derive this Poisson's equation? So, the Poisson's equation, you can get the mathematical expression for the Poisson's equation as, from the Gauss's law. What is Gauss's law? The differential form of Gauss's law is del dot E is equal to rho by epsilon 0. And we know that this electric field, we have defined this electric field as a negative gradient of potential V. Now, substitute this equation number 1 and this is equation number 2. Now, substitute 2 in 1. On substitution, you will get as del dot minus del V is equal to rho by epsilon 0, which is equal to minus, what is del dot del V, which is nothing but del square V is equal to rho by epsilon 0, that is del square V is equal to minus rho by epsilon 0, minus rho by epsilon 0. So, this is called the Poisson's equation. If the charge density is 0, if the charge density is 0, that is rho is equal to 0, then the Poisson's equation will become del square V is equal to 0, and that this is called the Laplace equation. This is called the Laplace equation, and in the coming chapters we will discuss more about this Poisson's equation and the uses of this Laplace equation. Now, we will check if there are n number of charges, what is the expression for that potential, and this is actually a superposition principle regarding the potential. If there are n number of charges q1, q2, q3 and up to qn, and I want to find out what is the potential at this point P, I should consider the electric field produced by the we know that since this field is a vector field, I can add E is equal to E1 plus E2 plus E3 up to En. This we are discussing the superposition principle. So, what is the potential produced at the point P? The potential produced, V is equal to, the general expression is equal to minus integral to the from the reference point, the point in the E, the electric field E, into E dot dl. E dot dl. This is the general expression for the potential. Now, we know that the total electric field is nothing but integral from the reference point to the point E. E is equal to E1 plus E2 plus E3 up to En dot dl. Now, I can split these terms and I will get it as integral from reference point to the point in the E, which is the point P, into E1 dot dl plus this minus is a common factor. So, I can take this outside, and which is equal to reference point to the point P, E2 dot dl plus integral reference point to the point P into E3 dot dl up to reference point to the P En dot dl. Now, we will close this bracket. What is minus integral E1 dot dl minus integral E2 dot dl? Like that, I can write it as, which is equal to V1 plus V2 plus V3 up to Vn. So, the potential at a point P is the sum of the potential due to individual charges, the potential produced or the obtained due to the individual charges. Similarly, in the case of a superposition principle regarding the electric field at a certain point is defined as, or it is the sum of, algebraic sum of the field produced due to individual charges. Now, if the charges are a continuous one, I can write it as, or V, this V I can write it as V is equal to sigma V I. If there are n charges I runs from 1 to n, then V is equal to sigma I is equal to 1 to n V I. So, in general I can write V is equal to sigma I is equal to 1 to n V I. Now, what is, if the charges are a continuous one, this sigma V I is equal to dV, sigma V I is equal to dV, where dV represents the continuous for a continuous charge distribution. And we know that according to the Poisson's equation, del square V is equal to minus rho by epsilon 0. So, what is the advantage of this Poisson's equation? On integrating this equation with respect to rho, we will get actually the value of the potential. So, in the case of an volume charge distribution rho, what is the total charge? The total charge or the small charge dq is equal to rho d2. This is by definition. So, dq by or integral dq is equal to integral rho d2. So, how can I write for a continuous charge distribution? If this is a continuous charge distribution, what is the potential produced at this point P? I can write this dV is equal to 1 by 4 pi epsilon 0 dq by r, dq by r. So, for this volume charge distribution, dq can be written as rho d2. So, dV is equal to 1 by 4 pi epsilon 0 not the integral rho d2 by r. So, what is the total potential produced due to this volume charge distribution? The volume charge distribution, the total potential V is equal to integral 1 by 4 pi epsilon 0 rho d2 by r, rho d2 by r. What about for a surface charge distribution? If the surface charge density is sigma, if the surface charge density is sigma, then dq is equal to sigma d, sigma d. So, I can write it as dV is equal to 1 by 4 pi epsilon 0, 1 by 4 pi epsilon 0 dq by r. This is due to the point P, due to this surface charge, the potential at this point P due to this surface charge distribution. So, according to this surface charge distribution, dV is equal to 1 by 4 pi epsilon 0 dq by r, and I am substituting for dq as 1 by 4 pi epsilon 0 sigma dA by r. So, the total potential V is equal to integral dV is equal to integral 1 by 4 pi epsilon 0 sigma dA by r, and the potential due to the surface charge density is equal to integral 1 by 4 pi epsilon 0 sigma dA by r, 1 by 4 pi epsilon 0 sigma dA by r, and this is due to the, this is the volume distribution rho. And if the charges are arranged in a linear way, and if the linear charge distribution is lambda, I can write dq is equal to lambda dl, and V linear is equal to integral 1 by 4 pi epsilon 0 lambda dq by r. So, what is dq actually, which is equal to lambda dl, which is equal to integral 1 by 4 pi epsilon 0 lambda dl by r. This is the potential due to the linear charge distribution. And in the same case, we have written or we have derived the situation for the volume charge distribution as, the electric field as V is equal to integral 1 by 4 pi epsilon 0 sigma dA by r for the volume charge 1 by 4 pi epsilon 0 rho d tau by r, and for the linear 1 by 4 pi epsilon 0 lambda dl by r. And in the first lecture, we have derived for the electric field for the same volume charge, linear charge, and for the surface charge. So, I will rewrite these three equations as, for in the case of a potential V for the volume charge distribution as is equal to 1 by 4 pi epsilon 0 integral rho d tau by r, and V for the surface charge distribution, which is equal to 1 by 4 pi epsilon 0 integral sigma dA by r, and V at the linear charge distribution, which is equal to 1 by 4 pi epsilon 0 integral lambda dl by r. And similarly, the electric field E is equal to 1 by 4 pi epsilon 0 integral rho d tau by r square into r cap plus E at the surface is equal to 1 by 4 pi epsilon 0 into sigma dA by r square into r cap into E at the linear charge distribution is equal to 1 by 4 pi epsilon 0 sigma lambda dl by r square into r cap. So, what is the main difference between these three or these six equation? The electric field is depending upon the r cap, which is the unit vector along the radial line. And in the case of this potential is a scalar quantity. So, from this equation, E is equal to minus del V. From this equation, E is equal to minus del V. You can easily find out what is E. What is E? Because V is a scalar thing. V is a scalar thing. And in each cases, and you want to find out what is the direction of the field. Otherwise, you should find out what is the charge distribution and what is the radial vector along that direction. So, this is the main disadvantages of this field formulation. You can't, you should define what is the direction of r cap. But in this case, this V is most, or since V is a scalar quantity, we can easily determine E from this equation. So, this is the main advantage of potential formulation. And again repeating, what is the main advantage of this potential formulation is, this potential is defined as 1 by 4 pi epsilon 0 integral rho d tau by r. And from this equation, the negative electric field is defined as the negative gradient of this potential. From these two equations, it is clear that the potential only depends upon a scalar quantity, while the field depends upon vector quantity, where this vector is this r cap, and r cap is a unit vector in the direction of this radial vector connecting the source charge and the point. So, a vector problem can be reduced to a scalar problem if the potential is determined instead of field. This is a very simple method, as there is no need to know about the vector component and the vector operations. After knowing the potential, intensity of the field can be determined as a final result using this equation 2. So, this is the main advantages of this potential formulation, and this is why we are learning this potential in detail. So, according to this, if there is no charge density, del square V is equal to 0. This is called Laplace equation. Laplace equation has more solution in 1 dimension, 2 dimension and 3 dimensional cases that we will discuss in the coming chapters. Hope you have enjoyed this session. See you next time. Until then, goodbye.